Our galaxy contains between 100 and 400 billion stars. There might be as many as 400 billion planets in the Milky Way alone if each star has only one planet. Now think about this. There are approximately 2 trillion galaxies in the universe, which indicates that there are a tremendously large number of stars in the universe. According to some estimations, there are even more stars in the universe than there are grains of sand on all the beaches on Earth. That might indicate an equal number of planets. But here's the strange part. Despite all these possibilities, we haven't received any signals from extraterrestrial life. There's no solid evidence that they're out there trying to communicate with us. This weird situation, where the odds of finding alien life seem high, but we have no proof, is called the Fermi paradox. It asks the simple but profound question, where is everyone? Scientists may now have found a hint that will help them solve this riddle. They have found that our galaxy is located close to the center of a huge cosmic void called the local hole or KBC void. Some of the most fundamental concepts in cosmology are called into question by this emptiness, which spans an astounding 2 billion light-years vast. Big concerns concerning the Big Bang, the distribution of galaxies, and the nature of the universe's expansion are brought up by the discovery of such a massive, empty region. The most exciting aspect, though, is that this gap may provide insight into the Fermi paradox and the Hubble tension, two of astronomy's greatest mysteries. So how did astronomers figure out that we live in a mysterious cosmic void? How does the KBC void challenge our standard model of cosmology? And most importantly, how could it explain why we haven't received a message from another civilization yet? Astronomers discovered the KBC void by examining the distribution of galaxies in the nearby universe. This groundbreaking discovery was made by Ryan Keenan, Amy Barger, and Lennox Cowie. Galaxy redshift studies, which quantify the shift in galaxies' light caused by the expansion of the universe, were employed by the researchers. They were able to identify areas with fewer galaxies by using this technique to produce a three-dimensional map of galaxy distribution. They discovered a spherical region about 2 billion light-years across that is significantly devoid of galaxies in comparison to the surrounding regions. The size of this vacuum is around 7 times that of a normal cosmic void. At first, researchers were skeptical about the existence of such a void because it poses significant challenges to the standard model of cosmology. There are 2 main problems. The first is the cosmological principle. The significant lack of galaxies in the local hole challenges the idea that matter is evenly spread across the universe, a key assumption in our current understanding of cosmology. The second problem is simulations. Cosmological simulations like the MXXL simulation suggest that forming a void as large as the KBC void is unlikely under our currently accepted lambda CDM model of the universe. According to these simulations, the gravitational forces predicted by this model aren't strong enough to create such a vast and deep underdensity. But as more information and observations were gathered, it became clear that this enormous vacuum existed. This 2 billion light-year wide region has been routinely shown to be significantly devoid of galaxies by surveys and telescopes. However, astronomers quickly discovered that although this gap initially presented a hurdle for our models, it might possibly hold the solution to one of the most significant cosmological problems, the Hubble tension, which has baffled scientists for more than 60 years. The Hubble tension, the largest cosmological crisis, might be resolved by the fact that we are close to the middle of a massive cosmic emptiness. Hubble tension refers to a puzzling disagreement about how fast the universe is expanding. To understand this, let's break it down. The universe has been expanding since the Big Bang, and the rate of this expansion is described by a number called the Hubble constant. Think of it as a speed limit for how fast galaxies are moving away from each other as the universe grows. There are 2 ways to measure this expansion. The first one is the direct method. This involves looking at nearby galaxies. Astronomers use special types of variable stars and supernovas to calculate distances in space. Then they measure how fast these galaxies are moving away from us. This gives one value for the Hubble constant. The second one is the indirect method. This involves looking at the cosmic microwave background, the afterglow of the Big Bang. This light has been traveling for over 13.6 billion years and gives us a snapshot of the early universe. Using a detailed model of how the universe has evolved since then, scientists can estimate what the Hubble constant should be today. Here's where the tension comes in. The Hubble constant calculated from nearby galaxies is about 73 kilometers per second per megaparsecs. The value estimated from the early universe is about 67 kilometers per second per megaparsecs. This discrepancy may seem small, but it is statistically significant and well beyond the expected margin of error. Additionally, it adds uncertainty to our estimate of the universe's age. Running the clock backward on the expansion is a common method for estimating age. The time since the Big Bang can be calculated by estimating how long the universe has been expanding to reach its current size based on how quickly it is now expanding. A greater value of the Hubble constant indicates that the universe is around 12.5 billion years old. An age of 13.8 billion years is suggested by a lower Hubble constant. This results in a startling 10% disparity. The Hubble tension is a big deal because it suggests that something might be missing or misunderstood in our current understanding of the universe. It could mean that there's new physics to discover, something beyond what we know about dark energy, dark matter, or even the nature of gravity. However, another simple explanation to the Hubble tension is our unusual place in the universe. There are fewer galaxies and matter inside the KBC void than outside of it. Because of the void's reduced density, objects within it exert less gravitational attraction, but the surrounding, denser regions exert a stronger gravitational force, attracting objects to them. This gives the impression that the local universe is growing faster than it actually is because we are being drawn by the gravity of objects outside the void. When scientists analyzed the matter density inside the KBC void up to a distance of 300 megaparsecs, they found it to be about 20% less than the universe's average density on larger scales. This lower density within the void correlates with previous studies showing that the expansion rate measured locally is about 11% greater than the true expansion rate. Essentially, the gravitational effects of the denser regions outside the void give us the impression of a faster expansion, which could explain the Hubble tension. The presence of the KBC void calls into question the lambda cold dark matter concept, which is the most widely accepted and successful description of the universe. Based on early universe density fluctuations and the uniform distribution of matter on large scales, this model does not foresee the emergence of such enormous empty zones. However, when scientists altered the initial density fluctuations and improved the efficiency of structure development in their simulations, they discovered that voids such as KBC may arise. However, there was a catch. Their simulations no longer matched the LCDM model. Instead, they employed an alternate theory known as modified Newtonian dynamics, or MOND. MOND, which was originally proposed to explain the unusual behavior of galaxy rotation curves without admitting dark matter, proposes changing Newton's law of gravity rather than introducing unseen stuff. The two primary differences between LCDM and MOND are as follows. First, MOND eliminates the necessity for dark matter by changing the way gravity functions at low accelerations. Second, MOND predicts that galaxy and galaxy cluster growth occurs more quickly than in the LCDM model. This rapid structure development increases the likelihood of voids in a MOND world. The tension between these two theories remains unresolved because some cosmic observations support MOND, while others align with the LCDM model. As a result, there is no clear winner in the debate between these two competing ideas, leaving us with an ongoing mystery about the true nature of the universe. The finding of the KBC void suggests that certain cosmological assumptions may need to be updated or abandoned in light of new data. If the universe exhibits considerable local density changes, key cosmological assumptions and models, such as those concerning dark energy and cosmic structure development, may need to be reevaluated. Living in the KBC void offers a new viewpoint on the Fermi paradox, which asks why, despite the vastness of the cosmos and the high probability of extraterrestrial civilizations, we have failed to discover definitive evidence of their existence. There are three main points. The first is isolation. The KBC void is a vast, underpopulated region of the universe with far fewer galaxies and therefore fewer stars compared to denser areas. This isolation could mean that intelligent civilizations are less likely to be found in such voids. If life is more common in denser regions, our position within the KBC void might place us far away from other civilizations, making it much less likely for us to make contact or detect signs of their existence. The second category is distance and cosmic scale. The vast distances between sparse galaxies, particularly in a void like KBC, can cause severe delays in communication and movement. Even if advanced civilizations exist nearby, the vastness of the vacuum may mean that their signals are too far away to reach us in a reasonable timescale. This supports the view that, while intelligent life may be numerous, the distances involved make direct interaction extremely unlikely. The third is avoidance. Civilizations may choose to avoid contact with less advanced societies or might simply be unaware of our existence due to our location in a sparsely populated area like the KBC void. The characteristics of this void suggest that intelligent life is more likely to develop in crowded regions of the universe, where resources and interaction are more abundant. As a result, these civilizations might overlook or not prioritize exploring less populated regions like ours, making contact with us less likely. This perspective provides a likely explanation for the Fermi paradox, highlighting that while intelligent life may exist, our position in a vast, empty region of the universe may render us largely disconnected from it. The KBC void also has anthropological considerations. The anthropic principle asserts that the universe seems as it does because we, as observers, exist to view it. In the context of the KBC void, it means that our presence in a low-density region of space is not a coincidence, but rather a required requirement for the evolution of life as we know it. If the cosmos were evenly thick or lacking huge holes, the circumstances for life might not have existed, and we would not be here to witness it. Thus, the KBC void's properties, like its size and relative emptiness, are not aberrations, but rather a normal consequence of the universe's structure, which allows for the presence of observers like ourselves. Even though it sounds exciting, the scientific validity of the anthropic principle is often debated because it can sometimes be seen as more of a philosophical argument than a scientific hypothesis. Nevertheless, the KBC void has added a new layer of mystery and intrigue to understanding how the universe works and our place in it. It will be interesting to see if it can really become the ultimate answer to the Hubble tension, one of cosmology's biggest mysteries.